an unperturbed AdS phi cross S phi background, where I emphasize this is the global AdS phi. So again, in my picture, global AdS phi is just a soup can with metric okay. So this is the Lorentzian geometry, and I'm going to give you a simple argument momentarily to convince you that black holes fit very naturally into this framework. And in order to do that, I'm going to, for a short while, maybe 10 minutes or so, switch out of the Lorentzian framework and talk about Euclidean geometries for the moment. I'll switch back and forth between the Lorentzian and Euclidean geometries because it's much easier to define states and talk about properties of states in the Euclidean geometry. Okay. So let's look at this theory at finite temperature. That is, I'll work in a canonical ensemble and I want to know what are the relevant geometries I need to consider if I want to figure out what the physics of n equals 4 Soup-Yang Mills at any finite value of temperature is. Okay. So the first rule of the game I need to tell you, this is something you've heard, but I never enunciated it clearly, which is the thermal physics is equivalent to studying n equals 4 not on R cross S3 but on a circle whose periodicity is set by the temperature. Beta is 1 over temperature times the 3 manifold S3. Okay. Now, of course, there's something interesting here because the S3 has a scale, the radius of curvature, which I'll call beta tilde, and although the theory was conformal, now I have it on a background where there are two length scales. So the relevant dimensionless parameter I can tune is a ratio of scales beta over beta tilde. Now clearly small beta is the same as large beta tilde. I could take this, either take small beta, i.e. high temperature, or scale up my 3 sphere. Now what do I need to do if I want to find the dual geometry? The rules of AdS CFT say the following: find bulk spacetime geometries which have as boundary the manifold on which I am putting the conformal field here, which in this case is a product of a circle and a 3 sphere. And in all the discussion we had so far, I was talking about the vacuum state. There was only one relevant geometry, but here something interesting happens. I have two candidate geometries which extend into the bulk given this particular boundary. I'll give them names and then describe to you what the two geometries are. The first one is very simple. It's just what I call thermal AdS5. It's just the Euclidean AdS5 geometry where this Euclidean time has period B. The second geometry is much more interesting and is the starting point of what we are going to do later. Is the Euclidean Schwarzschild radius black hole. And again, let me tell you what it looks like. It's easy to write down a metric in the same coordinates that I have above. R is the radial coordinate and TE is Euclidean time, where this function f is given as follows. Okay? Now, it's exactly what you would write for a Schwarzschild black hole in 5 dimensions, except that it's in AdS. So this 1 plus r squared refers to the fact that this is a black hole in AdS, and the 1 over r squared is the right fall off of Newtonian potentials in 5 dimensions. And I have just parameterized what usually you would write the mass in terms of a parameter r plus, because it's much easier to talk of where the horizon of the black hole is located. The horizon of the black hole would be located, if it was a Lorentzian geometry, at r equals r plus, and the mass is determined by the size at r plus. So what does this geometry look like? This is a Euclidean geometry. It looks like a cigar. Where here the cross sections are these tau circles, which are flaring out because as r gets large, the circle gets big. As r goes to infinity, the circle gets big, but the circle shrinks at r equals r plus. And this if I were working with the Lorentzian geometry, is the location of the horizon. And to go to the Lorentzian geometry is trivial. I just take TE and big rotate it to I times T. Okay? So instead of having plus f of r dTe squared, the Lorentzian geometry has minus f of r dt squared.
Is f of r supposed to have a 0 at r equals r plus, so that the circle shrinks to 0 size?
Sorry?
Is f of r supposed to have a 0 at r equals r plus?
Yes.
It's suggested by the...
Yes, it will.
Yeah.
Sorry. Thanks. It's a fault of not keeping track of AdS radius in general. Okay. So you've seen an analog of this geometry in the case of the Poincare coordinates in Larry's lectures, and he outlined for you how you should think about this geometry. You see, the circle here is shrinking to 0 at r equals r plus, and I want to make sure that this is a smooth manifold. In order for this manifold to be smooth, I have to ensure that the periodicity of this TE coordinate in the Schwarzschild black hole is appropriate so that the circle shrinks as if this were an origin in 2 dimensions. Otherwise, I'll be left with a conical singularity, and I will leave you to work out that regularity demands that the TE coordinate has a period beta, which is given as follows. Okay, so you don't need to do very much. Take this metric, take the first 2 terms, expand the functions here f of r in Taylor expansion around r equals r plus, and then rewrite it in a fashion that looks like you're in flat space. So you should get some metric d epsilon squared plus epsilon squared let me write it as chi, makes it a bit clearer. Where chi has period 0 2 pi. Okay, so chi is related to tau by some simple scaling. Okay, and let's step back a moment and think about where do these two geometries come from. The thing is, I have a boundary which is S1 cross S3, and I want a 5 manifold which has this guy as a boundary. So I could take either the S3 and fill it in to be the boundary of a 4 ball, or I could take this S1 and fill it in to be a boundary of a deformed 2 ball, i.e. the cigar, and the 2 geometries come by the 2 choices I have of how to fill in this 4 manifold to make a bulk geometry. But the non-trivial question we are left with now is which of these 2 geometries are relevant for describing thermal physics. And the answer is actually quite interesting. The answer turns out to depend on which regime in parameter space you're in. So I said we have a dimensionless parameter. Depending on whether that parameter is small or large, one or the other of these geometries is relevant. And how do we find this out? We figure this out by looking in the sort of, so stepping back a bit, yesterday I gave you, or a couple of days ago, I gave you a prescription for computing correlation functions of operators in the field theory. The very same prescription you could use to compute the partition function of the field theory, which corresponds to having no operators inserted. So I just need to know, I could compute the partition function by using the supergravity approximation, and then use that partition function to compute a free energy. I could then ask, in a standard statistical sense, which of the 2 configurations I have has lower free energy. That's the configuration that's relevant for the regime of interest. So what we do is we compute this by computing the action of Euclidean gravity on the 2 solutions. That is literally you take the Einstein-Hilbert Lagrangian, plug in these two solutions, and evaluate the action on the solutions. And I'll give you the answer. For the difference of the black hole geometry and the thermal AdS geometries, and then tell you one subtlety in how I compute this. Okay, so this is the answer as a function of the AdS radius capital R and R plus, which is the black hole size. So what did I do in computing this? You see, for the black hole geometry, the periodicity was fixed. It was fixed by the fact that I had a parameter R plus. It was completely determined by R plus. And that came because I wanted a smooth geometry. For the thermal AdS geometry, I could have taken any period that I wanted. There was a priori no restriction on what period I could have chosen. So what's being done here is looking at the geometry at some large value of the radial coordinate r and demanding that the proper size of the time circle in the thermal AdS geometry and the proper size of the time circle in the black hole geometry agree. So I fixed the parameter in the thermal AdS side by this matching condition here, and then I can subtract the two answers. I'm evaluating the action with a cutoff, and I can get an unambiguously appropriate answer. But what do we have now? So this is the answer. What do we learn from this? We see that the action difference is such that for R plus bigger than R, the free energy, which in my notation is just S here, is such that the black hole dominates the ensemble. On the contrary, in the opposite regime, it's the thermal AdS that wins. Okay, so this is sort of standard statistical mechanics. I look at two configurations, I look at which has more free energy, and then infer from that in one regime I should be talking about the black hole, and in another regime I should be talking about thermal AdS. And now let's go back and make contact with our parameter there. R plus is just another name for the temperature, because the temperature is completely determined by R plus. I've just relabeled the scale, and so beta can be traded for R plus, and beta tilde, which was the size of the 3-sphere in AdS, on the boundary is exactly of size R. Okay, so I didn't write those scales before, but the two scales, the ratio of scales there is just the same as the ratio of scales of R plus over R. So as I dial this my parameter, I go from one regime where thermal AdS dominates the ensemble to a regime where the black hole dominates the ensemble. What's happening here is that there is a phase transition at R plus of order R, or in units of temperature, it's temperature of order 1 in AdS units. Now, someone should put up their hand and say, but this can't happen. I'm talking about a field theory in finite volume, which means I'm not taking a thermodynamic limit. So why do we have a phase transition? The reason we have a phase transition has to do with the fact that I'm working in a limit where gravity is a good approximation, i.e. I'm working at large lambda and large n. Large n means that the number of species I have of objects in my theory is large. So I'm not taking a thermodynamic limit by taking my system size, the volume, to infinity, but rather taking the thermodynamic limit by taking the large n limit. So the parameter that's controlling the thermodynamic limit is n, not spatial volume, as you are conventionally used to in ordinary discussions of thermodynamics. And this phase transition has a name. It's called the Hawking-Page transition. And in n equals 4, you could also think of it as a confinement-deconfinement transition. And now,
when was it discovered?
the Hawking-Page transition?
Yeah,
It was way back in the 80s, I believe it was about
what
84.
was the interpretation of this phase transition? The volume was finite and there was no idea that the well-field theory has large and limited.
Okay, so when Hawking and Page discussed this, they were worried about Euclidean quantum gravity. So they were doing this in the context of Euclidean quantum gravity, and they precisely did that calculation up there. Now, it's a question of how you interpret the Euclidean quantum gravity action. So it's well known that it suffers from various problems, from the fact that the kinetic term for the scale factor has a wrong sign, and so on. So the interpretation of this is most solid if you can map this to a system that you know well and can understand it from ordinary field theory rules. In this case, n equals 4.
Sure, but n equals 4 is just after this. And
Yes.
when they did this, they named this phase transition, but they have no the thermodynamical limit.
No, they certainly didn't have a thermodynamic limit.
What was the limit?
So what they were thinking of was that if you were doing Euclidean quantum gravity, then you would look at all saddle points to the action functional. And there was one regime where the dominant saddle was thermal AdS, and another regime where the dominant saddle was the black hole. And that's it. There's no phase transition. It's just a question of which saddle dominates in which regime. The interpretation of the phase transition, I think, is more solid if you think about a large n field theory. And now I come back to qualify the statement I just made, that this is a confinement-deconfinement transition. And again, you're supposed to do a double take and say, but this was n equals 4 super Young-Mills, there is no confinement. It's a conformal field theory. So what do I mean by that? So you count the free energy in thermal AdS is of order 1, okay, in units of n. Whereas the free energy in the black hole geometry is of order n squared. So it follows, if you play around with the formula given up and writing everything in terms of the 't Hooft coupling and n, but take my word for it, you can check that there is this behavior of free energy in the two regimes. And this is what I mean by confinement and deconfinement, that in the confined phase, which I'm going to call the phase dominated by the thermal AdS, it looks like the constituents of n equals 4 are bound together to give me excitations which are the number of degrees of freedom scales like 1 in units of n. Whereas when I move to the phase which is dominated by the black hole, it looks like I can see all the n squared degrees of freedom, all the gluonic degrees of freedom. And it's in this sense you should think of this as a confinement deconfinement transition. So there's a more refined discussion in terms of other order parameters that you've already seen, like Wilson loops, Polyakov loops, and so on. But I'm not going to get into that discussion today.
But if you have this picture with branes, then the number of degrees of freedom scales as n squared, yeah?
Yes.
And what is the interpretation using this dual picture of this confining phase?
In the field theory or in terms of the branes?
In the field.
So in the field theory, the picture is the n squared degrees of freedom I have on the branes.
Yeah.
I should just think of them as sort of gluonic degrees of freedom. Okay. So if I sort of look at the phase, so now let me quickly tell you what this phase corresponds to in terms of temperature. The black hole phase, if you sort of go back and ask where it starts dominating, when R plus is bigger than R, beta is smaller than 1. So you'll start seeing that this is the high temperature phase. Okay, so I should say this before I. Whereas the opposite limit is the low temperature phase. So in the high temperature phase, you heat up your system to very high temperature, and you start seeing that your system really has n squared degrees of freedom. That's what I mean by deconfinement. So you start seeing the individual excitations of all the open strings in the d brane. Whereas if you're in the low temperature phase, these guys excite only collectively. They sort of act as one coherent. Effectively, you get only 1 degree of freedom, not n squared. Now, how to see this in the field theory, and whether if you were to work in weak coupling field theory, you would see such a behavior, I believe Shiraz Minwala will describe to you in greater detail next week. So indeed, if you sort of work at zero coupling field theory, you see exactly the same feature, that there is a phase transition where the free energy goes from order 1 to order n squared in n equals 4 super Young mills on a 3 scale. Okay.
This is different if you go to field theory on S1 cross R3, right? Because they're always the black hole.
Exactly. So why is that? So what does it mean to go to S1 cross R3? So going to R3 means I need to take beta tilde large. Or said other words, the parameter up there, beta, or the ratio of scales, is being made small. It's equivalent to taking beta to 0, i.e. going to high temperature. So whenever you go to the planar theory, the theory on R cross S3, you're always in the high temperature phase. You're never in the low temperature phase. Exactly. Okay. So that accomplishes the first part of my discussion, which was to show you in what context do black holes show up in the AdS CFT correspondence. Okay. Having done all this discussion in the Euclidean case, I'm now going to switch into the Lorentzian AdS CFT discussion. Now, why do I want to do this? Okay, so this is my Lorentzian black hole. I took my black hole solution, which I had a couple of moments ago, and flipped the time coordinate to get a Lorentzian solution, where f of r is still the same guy we had before. And of course, now the interpretation of the geometry is different. This is a Lorentzian geometry with a black hole horizon and singularities. So the Euclidean geometry, roughly speaking, ended when R hit R plus. That's not true for the Lorentzian geometry. And the simplest way I know how to visualize the Lorentzian geometry is to draw a Penrose diagram, which is what I'm going to do. So you've all seen a Penrose diagram for Schwarzschild black holes. This is too wide. And I claim that this is the Penrose diagram for a Schwarzschild AdS 5 black hole. And I've intentionally drawn the singularity with this curvature, which is going to play a role in what I have to say later. So what do I have? The coordinates in which I've written the metric are basically speaking good only outside my horizon. This is R equals infinity, the boundary, the standard AdS boundary that you've seen before, and constant R slices march me inward until I hit the horizon at R equals R plus. And why is this a horizon? It's a horizon because the killing field d by dt becomes null at that point. The time, on the other hand, constant time slices in this geometry, they march up in this fashion with t equals infinity being the future event horizon and t equals minus infinity being the past event horizon. And of course, we all know that there's nothing special about the event horizon. You can continue your coordinates past, it's just some coordinate singularity, an artifact of the fact that I chose to describe this Lorentzian space with a poor choice of coordinates, and we encounter a curvature singularity at R equals 0. Now, that's what is, and the sort of the other part of the Penrose diagram is just the other asymptotic region I would get to by going through spatially through the stuff that's on the other side of the Einstein-Rosen bridge in standard Schwarzschild. Okay. Now, the nice thing about what I just said is that we have some feeling of how we should think about this black hole in the field theory. It's just the field theory heated up to some finite temperature. And now if I know what I am talking about in the field theory, I can of course now start asking interesting questions in the field theory, which are things I would like to answer, which is, this is a geometry which classically is singular. There is a space-like singularity at R equals 0. Does the field theory fix it? If I describe this black hole in terms of the field theory, can I check that the field theory description is which I should take to be the complete non-perturbative description of quantum gravity? Does that regulate the singularity in some nice fashion? There's another interesting sort of structure, which is the event horizon, which is a causal barrier which prevents stuff which is inside the black hole from communicating with the observer sitting out at infinity. What is that in the field theory? How do I think about that in the field theory? Can we identify these objects which we are familiar with from a classical perspective of thinking about black holes in classical general relativity from a completely field theoretic perspective, because the AdS CFT correspondence is supposed to give us a complete picture of quantum gravity in antidistributed spaces using n equals 4 super Young mills. So what I'm going to do now is describe a couple of attempts to try to understand some of these features from the field theory. And before I sort of get into sort of the details of how we would look at these, what in the field theory would know about the singularity, or what in the field theory would know about the event horizon, I want to try to convince you that the presence of an event horizon is not a barrier to obtaining information about the region of the geometry inside. You see, usually we would say we have a space-time with an event horizon. The field theory is supposed to live on the boundary. So in a sort of standard sense, there's a black hole way out there. We are boundary observers. All we see is stuff that's outside the event horizon. This is causality in this geometry. So then we have to start wondering, if we have a causal barrier, the event horizon, how are we going to obtain information from behind the horizon? The field theory is manifestly causal. It obeys standard laws of causal relativistic quantum field theories. So we shouldn't be doing something fishy in extracting behind the horizon physics. And the thing that saves us is that in general relativity, there's nothing special about the event horizon. It's not a marked point on this manifold. There's absolutely nothing happening there. And further, it's a completely global concept. We sitting here should not be able to tell if someone is collapsing something from Andromeda or wherever and forming a black, which in the future would form a black hole, and we currently would be inside the event horizon of this black hole in the future. So let's try to do that, and let me give you a very clean argument which illustrates that AdS CFT ought to be able to describe behind the horizon physics in principle. I'm not going to give you a calculation because we don't know how to do this particular calculation, but it's a matter of principle argument which suggests that there is information of physics behind the horizon in the field theory. Okay, so let's do the following. So this is a Gedanken experiment which one day, if we can put into the form of a formal calculation, would serve to understand some of the mysteries of black holes very precisely in the context of AdS CFT. So let me start with my soup can picture. I'm going to start with vacuum AdS. And I have some point P somewhere in the bulk. Okay, something's happening at P. I just want to know. I want to be able to measure something happening at this space-time event P. Okay. Now, in order to make this argument for simplicity, I'm going to assume that I could measure whatever is at P by computing the expectation value of some non-local operator like a Wilson loop at an instant in time. So this picture is such that P is a space-time event, just a point, say at the origin of AdS. And at some time t, I compute a Wilson loop which is aware of the fact that there is a point P in the bulk. So I make this measurement so I know about P. Okay, I'm not telling you what information about P I have, but I know that there is stuff in AdS at this point P. Okay, so far I haven't done anything. I've just told you that I've extracted some information about a local point in the bulk. Now, Same picture, there's P, here's my measurement, my Wilson loop, but then a little while after I do the measurement, I'm going to take a huge shell of matter and implode it. I'm going to kick it in from the boundary, watch it implode and form a black hole. But I'm going to send in the shell after I have done my measurement. The shell falls in, makes a black hole, a singularity forms, and I want to know where the event horizon of this black hole is. I can wait for very long, sort of look at the null geodesics that are coming out, radially coming out, trace them back to the past, and figure out where the event horizon is. And I find that if my shell was big enough, my measurement happens to have been made at a point which was, technically speaking, inside the black hole. But I have violated no rules of the game in the process. It's a completely fine thing to do, make a measurement, and then decide to change the state by throwing in a shell. I form a black hole. But it remains a fact that point P lies inside a black hole. But I have information about point P in the field theory because I've already made my measurement. Okay? So this simple experiment illustrates that there should be no causal barrier to extracting information from behind the horizon. All I'm relying on here is the fact that the event horizon in a black hole is a completely global concept. There is no way locally, when I measured P.
Yeah, but here I assume that the event horizon has been formed. And
Yeah, so I'm going to collapse enough matter.
okay.
So if I didn't form an event horizon, then this was sort of a regular point, and I could have performed this experiment.
And what about field theory? If you have the black hole, just the normal AdS structure black hole.
Right. So that's the point I'm going to come to. So this procedure is well defined in the field theory. I'm giving you some quantity W, some Wilson loop, or some suitable operators whose expectation value you're supposed to compute. And then I have to turn on the right sort of operators which correspond to making a shell of matter in the bulk, collapsing it. And then you have to be able to know that you form a black hole. So in some sense, really in the field theory, it's a field theory in finite volume. If I throw in enough energy density in that field theory, it will eventually thermalize. And the late time behavior will look like that of a black hole. If I put in enough energy, it will form a big enough black hole to encompass this point inside the horizon. The problem here, of course, is that while this is a good calculation for me to illustrate the essential point, it's a calculation we don't know how to do in the field theory.
Sorry, could you go over exactly what the calculation is in the field theory?
Okay. So the calculation involves finding a class of suitably a suitable class of non-local operators, some sort of dressed Wilson loops, which in the AdS CFT literature in the past have been called precursors.
Is this a Wilson loop that goes around the equator of the S3, let's say, so it spans the whole?
It spans the whole AdS. Yeah. So you should be able to use that. And let's say what you want to sort of, well, the other thing I glossed over is that I want a suitably localized event in my space-time. Let's say I have a little bit of matter somewhere, and I want to collect information about how this matter is how encoded in AdS. And we very well know there's a problem there, which is the scale radius duality, which makes it hard for me to probe deep into the interior in the boundary. So the issues of principle in how I formulate this computation having to do with how the scale radius duality works and what precisely is the class of operators I need to work with. But
The idea is that the Wilson loop will be filled in by some space-like Euclidean
exactly.
spring world sheet
Exactly.
that reaches the
That reaches
fills
my
the
point,
whole of the,
and then it knows about the fact that there was something, say a flag stuck in at point P. And that's the information I really need. I need to know that there was a flag at point P. And that's enough, because if I know that there's a flag stuck at a point behind the horizon, in this context, I've extracted some information about physics behind the horizon. So, are there any questions about this? I'm now going to try to describe a slightly different context in which you can try to make some of these ideas a bit more precise. But I'm going to concentrate on a very particular aspect of the problem. Okay. So, as I just said, these computations are hard to do, and there's some generic point somewhere inside the horizon where stuff starts happening. I'm going to be hard pressed to extract that information and give it to you in terms of field theory quantities. However, I could sort of stop worrying about all these time-dependent processes where I make a measurement and subsequently collapse a black hole, wait for the black hole to settle down, and just take what I already have, the Schwarzschild AdS black hole, an eternal Schwarzschild black hole which is a staying pool. Okay? And I can ask, is there something, can I learn something about this? About some part of the geometry which is behind the horizon. And there's clearly one part of the geometry behind the horizon which is very interesting, which is the singularity. So I can now slightly change the rules of my game and say, can I use the spirit of this type of discussion, which tells me that I can probe behind the singularity, to go back to this setup and actually study what the meaning of the singularity is in the field theory. If I give you an observable in the field theory which is sensitive to the presence of the black hole singularity, I can then go away, compute it at weak coupling or wherever, and ask how does the singularity resolve itself when I take quantum gravity effects into account. Because after all, the AdS CFT correspondence gives me this geometry as a dual to the field theory at large lambda and large n. Quantum gravity corrections would be finite n and finite lambda corrections away from this point, where supergravity stops being a reliable approximation to the field theory. And we know that's true because if I want to look at small lambda and small n, SU2 gauge theory, SU2n equals 4 with some value of the 't Hooft coupling of order 0.1, I could just as well do perturbation theory. Okay. So let me describe for you a framework to probe the black hole singularity which involves taking the picture I drew up there very seriously. So far, I had my field theory living on one boundary, and we had the event horizon and the singularity behind the event horizon. I'm now going to suggest that we take this picture a bit more seriously. So what do I have here? I have two regions which are asymptotically AdS. I convinced you a while ago by comparing free energies in the Euclidean context that this geometry was dual to a thermal field theory, i.e. dual to working in the canonical ensemble. In the canonical ensemble, what I have is a density matrix which is e to the minus beta h, where beta is the inverse temperature and h is my CFT Hamiltonian. Okay? And the thermality comes because I have a density matrix. I now want to tell you to take the fact that we have two boundaries to this AdS spacetime seriously and think of not this density matrix in the CFT that lives on this boundary, but sort of unwrap this density matrix into something much simpler living on the two boundaries of this geometry. So both boundaries have the same structure. They both in the Lorentzian geometry time cross a 3-sphere. And I imagine that on this boundary, which I'll call boundary 1, there is a Hilbert space of the conformal field theory, and on boundary 2 there is an identical Hilbert space of the same conformal field theory. Okay? Nothing wrong in that. But what is this?
Not S1 crosses the boundary.
Sorry. So I switched from the Euclidean context to the Lorentzian context. In the Lorentzian context, time is not compact.
So now the temperature is still controlled by R plus, the value of R plus?
It's controlled by the value of R plus.
Right, so now you've got a non-compact
Exactly.
Lorentzian time direction.
Exactly. So the distinction you want to keep in mind is exactly what you usually think of. I mean, you can think of working in Euclidean compactified thermal coordinate when you want to do finite temperature physics, but in the real world, I mean, time is Lorentzian, time runs. We can just as well turn on temperature. So you can work with real non-compact time and do real-time physics, like what, for example, Larry was describing this morning, when you have a quark moving through a hot medium, which corresponds to doing real-time physics with finite temperature.
So somehow this setup is only available for a certain range of temperatures. Is that right?
Exactly.
In the high temperature phase.
Exactly. So I have to restrict myself to be in the high temperature phase in order for me to be able to talk about the black hole. And precisely.
Does anything, if you take the corresponding field theory setup with 2 copies of n equals 4,
Yes.
is it obvious that anything happens at the temperature where this picture starts to make no sense? I mean,
Yes. So at the point where there is a phase transition in the Lorentzian thing,
yes.
so we said it goes over to thermal AdS.
Yes.
So what I'm going to describe now is a way to think of this density matrix in terms of 2 copies of Hilbert spaces. I'm going to open out a density matrix and purify it. Okay. So what you should think of at the point where this picture starts making sense is that I have 2 AdS geometries which are entangled in a given fashion. So standard thing I would do if I were to sort of purify an entangled state. So which needs explanation. So let me get to that.
So this means that these two theories are somehow entangled.
So I'm going to describe exactly that entanglement.
What's the point of considering only one n equals 4 squared?
So let me get to it. So consider in this enlarged Hilbert space a pure, no quotes, entangled state. So the state psi, we consider some normalization states EI are energy eigenstates in one Hilbert space. I'm taking a state in the tensor product and I'm entangling them with a particular weight factor. The weight factor has been chosen such that if I took this state and traced over one Hilbert space, H2, I recover precisely the density matrix I wrote up there in the Hilbert space H1. Okay? So this has a name in real-time thermal physics. It's called the thermofield formalism, which is just you just double your degrees of freedom so that instead of working with density matrices, you work with pure states. Okay, you could always do this. It's just that working in the AdS CFT context gives me a geometric interpretation of this doubling trick. There are two natural places where my Hilbert spaces can live.
But you could do that in the field theory for any value of beta.
That's right.
But
So
your gravity picture only works for
exactly.
some
So
of the values.
right. So I could do this for any value of beta, but my gravity picture works as a single Lorentzian manifold for values of beta which are large, which are small, sorry, with high temperature. But for low temperature, I get two Lorentzian manifolds.
Oh, I see.
I get two copies of AdS geometries. So you should think of two disconnected Lorentzian geometries where I have by hand implemented this entanglement to define my state. And the rules of evolution here are that the Hamiltonian in the tensor product Hilbert space is nothing but Hamiltonian in the first minus the Hamiltonian in the second, because if you go back to the geometric picture, you find that time runs up on one side of the geometry and runs down on the other side of the geometry. Okay. The thing we are going to do is calculate correlation functions. This is what I discussed at length in the last couple of lectures. And we're just going to use simple 2-point functions to try to see if we can see the black hole singularity. So what kind of correlation functions can I compute? Well, I have two Hilbert spaces. I could either compute correlation functions with all operators from one Hilbert space, or I could compute mixed correlation functions with operators on both sides. So the operators I have at my hand are the ones in the first Hilbert space or in the second Hilbert space. and I could compute in the state psi that I picked this very particular state which has a name. I could compute a correlation function where one operator is inserted in Hilbert space H1, mark it off here, and another operator is inserted in Hilbert space H2. So it's a perfectly valid object to consider in this enlarged context. So the state is commonly referred to as a Hartle-Hawking state because since it gives you the right density matrix, is what would be called the Euclidean vacuum if you're working with the Euclidean AdS Schwarzschild geometry. But here's a trick, and the trick is the following. There's an analytic structure to this geometry, which I'll come to in a moment, which allows me to think of the following. Instead of computing a correlation function of operators inserted one at each boundary, I could compute a standard thermal correlation function where I insert both operators in the same boundary and then analytically continue one of the insertion points. So I claim that this correlation function I've written here is equal to the very same correlation to a different correlation function where both operators A1, A and B are inserted now in the same boundary. I evaluate the correlation function and then analytically continue the time variable by half an imaginary period. So why is this? This is easiest to think of geometrically. So let me draw the picture I drew earlier of the Euclidean cigar, where this was I remind you the Euclidean time coordinate. So here this is the Lorentzian time coordinate running up. The two times are related by a Wick rotation. The Euclidean time is I Lorentzian times the Lorentzian time. So I could go from this boundary to these boundaries along a spatial section like this. I say a constant time slice. But you see, the Euclidean time coordinate you should visualize as an by analytic continuation. If I sort of take this geometry and make T complex, the imaginary T contour goes out and comes out here. So if you look at this section, the Euclidean geometry, this is H1 and this is H2. A better way to say it is ask yourself the following question. The coordinate T is not well defined everywhere on this Lorentzian manifold. Okay, there's a coordinate singularity here. But what if I wanted to make it well defined? I could, if I gave it complex values, and in fact, if time was T here, if I gave him, let me say, if the imaginary part of time T was 0 here, which is what I would want, by going through the horizon along a radial null geodesic, you can ask what phase factor you pick up. You pick up a phase factor which gives you imaginary part of t equals I beta over 4. The calculation I have in mind is to calculate that integral and pick up the residue from the pole at r equals r plus. And here you can check if I get my conventions right. That in the part of the Lorentzian geometry associated with Hilbert space 2, the imaginary part of t precisely minus I beta over 2. So going from this end to this end is like analytically continuing half an imaginary period, which is exactly going halfway around Euclidean time circle in this geometry. So the claim is you can compute this correlation function very simply by doing the calculation in a thermal field theory and then taking one of your arguments and analytically continuing it. Okay, very good. Now, all we need to do is evaluate this correlation function. Okay? And nothing I said so far depended on what operators I took. Okay? This statement is true for any operator I would pick in the field theory. However, since I want some information about the singularity, I'm going to continue to work in the geometric picture of the black hole and try to get some sort of intuition of what kind of operators I should look at and where I should look at in the correlation functions of those operators to extract physics of the singularity. So it turns out to be simplest to use high dimension operators the operator dimensions I'm interested in are of order n.
Sorry, I'm confused. Are you talking now about operators on R4 in the standard picture, or are we still talking about?
I'm talking about operator insertions on S3.
On S3.
On S3.
Okay, so slightly different.
Yeah. So I'm not using this usual state operator correspondence.
Yeah. Right, okay.
But I'm going to look for correlation functions on S3.
Of operators on S3.
Although, going back to the earlier question that was raised about R3 versus S3, for the black hole case, I really want to be in the high temperature phase. So I could just as well be calculating correlation functions in R3 and the same things would happen.
Yeah.
So I could just do the usual correlation function in R3. The only point here is that I'm going to have to analytically continue time to imaginary values once I do the computation. So if I look at very high dimension operators of order n, one can use WKB to approximate the correlator. Okay, rather than doing an explicit calculation, I'm just going to try to argue that in the WKB approximation, you can see enough signatures.
So this will be a large lambda.
This is
computation also,
yes,
right? Yeah.
yes. So everything I'm saying is that large lambda, large n, and further I'm looking at very heavy operators. And the geometric side, let me continue. Keep drawing this too wide. Let me continue to think in terms of this double-sided picture, where I have operators inserted one on each boundary, and you can show, I won't go through the argument, that if I have two operators, one on each boundary, in this limit of WKB that I'm talking about here, the correlation function that I'm interested in is given by, so let me call that correlator C, is given by a geodesic approximation where mm is the mass of the field in supergravity dual to the operator in question, and this quantity L reg is a properly regularized length of a space like geodesic connecting the 2 points. Okay, so this is a claim. I unfortunately don't have time to show you why this is true, but roughly speaking, this is true in the standard sense of sort of Feynman representations of path integrals. You have 2 points, but I want to compute the correlator between. I just get the dominant contribution from the classical path. And the only classical paths that connect points on the two boundaries are space-like. Boundaries are causally separated. Okay. Now, what I'm going to do is insert, look at the following two-point function in the states psi, where my operators are inserted at time t and minus t minus I beta over 2. So you should think of this correlator as being evaluated in the state psi, and I can go away and look at all the geodesics that I find interesting, and this is a picture of how geodesics look in the Schwarzschild AdS background. Space like geodesics. I have fixed the relative separation in real time, so I'm just moving t down. And a very funny thing happens. There is a critical time Tc beyond which there is no geodesic connecting the points. And this geometrically has to do with the statement I mentioned, did not prove to you before, the fact that the singularity of this black hole is curved down. So this is supposed to be a null line at 45 degrees, but all my angles are wrong. So take my word for it. There is a critical time below which there is no geodesic connecting 2 points. And at that critical point, the space like geodesic has 0 proper length. Regularized length goes to 0. Yes?
Just such slow in geodesics. I mean, you would have to come out of either on the one or the other side of the event horizon.
These are space like geodesics.
Are you approximate the light cone from the space like side?
Yes. So everything. So there's a light cone here, but these are sort of space like geodesics that are inside, and in the limit, when t approaches Tc, they approach it from the space-like direction. You're completely right. If otherwise, by causality, there's nothing time-like connecting.
Are you almost done, Mukund, or do you need to?
No, I'll be done in 2 minutes.
Okay.
Okay. So we get a prediction from this WKB calculation which says that this correlator in the state psi has a pole as t goes to Tc. I think I misspoke a while ago. This regularized proper length diverges as t goes to Tc. The geodesic is null, but there's a infinite distance between the two boundaries.
M is the mass of the state, so that scales like NC. So
M scales like NC.
So it's the power involved scales.
Exactly. So, but this again is an artifact of the fact that I'm using WKB to do this. So if you want to look at finite M corrections, you could try doing the computation for heavy but not so heavy states in the field theory. Now this is the story from the geometric side. And now we should all be very happy saying, here I have given you an observable in the field theory, a 2-point function of nice well-defined local operators, which shows a singular behavior at some particular value of time, and that singular behavior in the geometry is a consequence of the black hole singularity. However, the story is a bit more complicated, and I don't have time to discuss the subtlety involved here. I'll tell you in words what is the issue. The issue here is that I use a WKB approximation. So I did a saddle point evaluation of this correlation function. What I didn't do is do the correct saddle point approximation. So it turns out that this Lorentzian geodesic is the dominant saddle of my saddle point, but it doesn't lie on the path of steepest descent. There are two other saddles which are subdominant but happen to lie on the path of steepest descent. And the way to see this is the fact that in the formulation I gave you earlier of the Hawking state, you can go away and try to compute the 2-point function and show that it's always bounded. The 2-point function is bounded from above by its value at zero time, and that's a finite quantity. So what's happening here is that the real saddle points that contribute to the correlation function are Euclidean geodesics, complex geodesics in this picture, not this Lorentzian geodesic. Nevertheless, this story is not empty, because if you have multiple competing saddle points and there's some analytic structure to the correlator, by performing an appropriate analytic continuation, you can recover this behavior. So the bottom line of what I'm trying to say just now in very short time is that there is a signature of the singularity in correlation functions. It's not as manifest as one would like it, because it's hidden behind some series of analytic continuations I would need to do to extract it. But in principle, if I give you the exact correlation function of very high dimension operators in the large n, large lambda theory, one should be able to test this exactly. And then if we did the computation in the finite and finite lambda theory, we should be able to go back and look at the place where we found the singularity and see how it got smoothed out. So that's the part of the program that hasn't been accomplished to date. Hopefully one of you will show us how to do it. Okay, so with that I'll stop.
Questions? So the association between the singularity and the correlation function certainly relies on this WKB approximation. So if you were to find that the singularity disappeared at finite n and finite lambda, might it not mean that not necessarily the singularity being smoothed out, but the association between the correlator and the singularity, which relied on the geodesic approximation?
So
logically, it's possible that that would be the thing that's.
So I think for finite n that's probably true. For finite lambda, I find that slightly harder to believe.
Yeah, large N controls WKB here in some sense because it's the mass of the particle. But
In some sense, that's right. But also the issue is what we discussed earlier, that there are two geometries that contribute. And one of them was dominant at high temperatures. And the relative domination was a factor of e to the minus n squared. At finite n, I would have to keep both contributions.
right.
And one geometry is explicitly not singular. So there's contamination from multiple geometries in addition to the corrections to this geodesic approximation.
Ah. No more questions then. Let's thank Mukund for a very nice series of lectures.